Okay. So before we start class, let's start with a discussion on the schedule. Okay. So we have class. Yes, I was just about to get to that. We have class today and tomorrow. All right, today I want to finish up what we're going to cover in chapter 1. Which means that tomorrow will be a review day, and then next week on Monday will be our first exam. Okay? All right. All right, so we'll discuss more about how the exam will work tomorrow when we do our review. Okay. Any general questions about that now that you want to ask? Or about anything?
Professor,
Yes.
will there be is it going to be a mix of short answer and multiple choice, or just like what is the layout?
Yes, that the layout will be multiple choice questions, and half the exam will be multiple choice, and half will be like long answer, like you have to show your work.
Okay, thank you.
Okay. Let's see here. Can you assign more homework problems? If you want, you can go through the chapters that we did and just do some more problems from the homework sections. If you can do like the even numbered problems, if you like. Okay. We'll just have a review. There will not be a mock exam. What percentage is this exam of the total grade, sir? I see. If you want to see the percentages, you can look back on the syllabus. It should be there. How many proofs will there be? I don't have an answer for you yet on that. We can discuss that maybe more tomorrow. Okay. The exam will not be on Blackboard. It's going to work a little differently. Like I said, we'll discuss that tomorrow. Okay. The even number problems do not have answers, but if you wanted to do practice more problems, you could practice by doing those. Okay. Okay. Any other questions? Exam is 20%. That sounds about right. What it says on the syllabus. Yeah. Okay. What program will be using to monitor the exam? All right. So let's discuss that now. Okay. How can I practice if I don't know if it's correct or not? You can try it, and then if you want to know, you can maybe send me an email, and if I have a chance, I will get back to you. Okay. What program are we using to monitor the test? Okay, so let's discuss that briefly. How the exam will work. Okay, we may have discussed this at the beginning of the semester. I don't remember at the moment. So what we'll do is during the exam will be during class time. We will meet on this link on Google Meet, like we usually do. At the beginning of class, I will send you the questions. Either I'll send you a link to the questions, or I'll post it for you somewhere, and you'll have access to it. Okay. You will, during the exam, you will write out all your answers. Like, as we said before, some of them will be multiple choice, some of them will be long answer. You write out all your answers. At the end of class, okay, you will either scan or take a picture of your answers, your written out answers, and you will email it to me at my email address. Okay. Preferably you will email it to me preferably as a PDF. If you don't know how to make it a PDF, that's fine. Okay. During the exam, how will I monitor you? So I need to proctor you during the exam. So what we're going to do is during the exam, I ask that you have your cameras turned on and that you be in view of the camera during the exam. Okay, so that way I can proctor you during the exam. Okay, so that's how the exam will work. Okay. Any questions on that? if you use a tablet, and you take the exam on the tablet, yeah, you just like you have to just make sure you're in view of the camera so that I can proctor you. Mics, no, you don't have to turn on your mic. Okay, any other questions? Okay. All right, so let's begin today's material. Okay. All right, and we'll discuss this again tomorrow. Okay, so last time we continued our discussion on proofs. Okay, we talked about the two types of indirect proofs, proof by contraposition. Okay, so we said we can use a proof by contraposition. We can use that method to prove conditional statements because a conditional statement is logically equivalent to its contrapositive. Okay, so if you want to prove the statement if P then Q, instead you can prove the statement if not Q, then not P. Okay. And we also discussed the proof by contradiction. Okay. So in a proof by contradiction, we show that the negation of the statement we're asked to prove is false, right? That the negation leads to a contradiction and therefore must be false, so that the original statement that we want to prove has to be true. Okay. And remember, we said that if you have a conditional statement, the negation is the same thing as P and not Q. Okay. All right. So that's basically what we covered last time. Does anyone have any questions that they would like to go over, or any homework questions? Okay. Number 7. If you didn't finish the homework questions, you can also ask them tomorrow during the review. Okay. All right, let's see. We have a question from section 1.5, 9, parts G and H. Okay, so let's go in order here. Let's start with question 7. I'm assuming that's from section 1.7, and then we'll do the next one. Okay, yeah, so let's do that one first. All right. So number 7 asks us to use a direct proof to show that every odd integer is the difference of two squares. Okay, so the statement is every odd integer is the difference of two squares. Okay, before we do the proof, let's rewrite that as a conditional statement. Okay, it's a conditional statement. As you get experience, you can sort of do proofs without having to rewrite the sentence. But let's rewrite it so we see the hypothesis and the conclusion. So we're saying we want to show that every odd integer is the difference of two squares. That's the same thing as saying if, let's create a variable. If n is odd, it's an odd integer, then n can be written as the difference of two squares. Okay, it's something squared minus something squared. Okay, So direct proof. We assume the hypothesis is true. Assume n is odd. Assume n is odd. Okay, by definition, if n is odd, then n equals to 2k plus 1 for some integer k. Okay. All right. We need to show that the hypothesis is true. So we're going to show that n can be written as the difference of two squares. Okay. Okay. So I start with our assumption that n equals to 2k plus 1, n is odd. Okay. All right. Now I'm going to do something a little bit, well, what might seem a little bit creative here. Okay. I'm going to manipulate this thing algebraically a little bit. I'm going to add k squared to this thing, okay? But I don't want to change the value. So if I add k squared, in order to keep the number the same, I also have to subtract k squared. Okay, for whatever the integer k is. So I haven't changed the value. It's the same number because whatever I added, I subtracted. K squared plus k squared minus k squared. Okay. Now, why did I do this? Remember, I want to show that n equals to a difference of two squares. That means I want to show it equals to something, an integer squared minus an integer squared. Okay, something squared minus something squared. Okay. If I factor k squared plus 2k plus 1, what do I get? What's k squared plus 2k plus 1 factor?
K plus 1, K minus 1? K plus.
Not exactly. It's k plus 1 squared. It's k plus 1 times k plus 1. Okay. So what do I have here? I have something squared. K plus 1 is an integer. It's a number. Squared. Minus an integer squared. I have something squared minus something squared. This is a difference of two squares. So n is a difference of two squares. Okay, so if n equals to 2k plus 1, I can write it as the same. That's the same thing as writing n equals k plus 1 squared minus k squared, something squared minus something squared. Yes, this is number 7. Okay, so where did this come from? So first of all, you agree with me that, hopefully you agree with me that 2k plus 1 equals to k plus 1 squared minus k squared. All right, you agree with me on that, I hope. Okay, good. Where did I come up with this? So it's a little bit of creative thinking. You have to think about it for a while. Another way of coming up with this, sort of where did this come from, is to sort of check out a couple of numbers, like the first few odd integers, and sort of see if a pattern emerges. Let me show you what I mean. Let's say I start with some actual numbers here. Let's say I start with, here, let's make a table. I'll have n. Here will be 2k plus 1. So this will be k. All right, let me do it this way. All right, let's start with 1. 1 is an odd integer. How do I write it in the form 2k plus 1? I have to write it as 2 times 0 plus 1. Okay, that gives me 1. In this case, k is 0. Okay, so how can I write 1 as a difference of two squares? Well, I can write it as 1 squared minus 0 squared. Okay. Right? 1 is a difference of 2 squares. 1 is equal to 1 squared minus 0 squared. Okay, do you see that? Are you with me on that? Okay, good. Okay, so let's keep doing this for the first couple of odd integers, and hopefully we'll see a pattern emerging. Okay, let's say n is 3, the next odd integer. How do I write 3 in the form of 2k plus 1? I've got to write it as 2 times 1 plus 1. So k in this instance is k is 1. Okay, how do I write 3 as a difference of 2 squares? 3 is equal to what squared minus what squared? Yeah, 2 and 1. 3 is equal to 2 squared minus 1 squared, right? 2 squared is 4 minus 1 squared, that's 4 minus 1, 3. Okay, let's keep going. Let's say I go to 5. Okay, 5 in the form of 2k plus 1, that's 2 times 2 plus 1, right? Notice that as k goes up by 1, my odd integers go up consecutively, right? So when k is 0, I'm at the first odd integer, 1. When k is 1, I get 3. When k is 2, I get 5. When k is 3, I'm going to get 7, and so on and so forth. Okay. So here k is 2. How do I write 5 as a difference of 2 squares? It's equal to what squared minus what squared? Exactly, 3 and 2. It's 3 squared minus 2 squared. Okay. 3 squared would be 9 minus 2 squared is 4. 9 minus 4 is 5. Okay, we'll do one more, and then hopefully you will see the pattern. Okay. All right, if I do 7, 7 is 2 times 3 plus 1. Okay, here k is 3. So how do I write 7 as a difference of 2 squares? This time it's what? What squared minus what squared? Hopefully you see the pattern by now. 1 was 1 squared minus 0 squared. 3 is 2 squared minus 1 squared. 5 is 3 squared minus 2 squared. 7 is what? Yes, exactly. 4 and 3. 4 squared minus 3 squared. Yep. Right, what's 4 squared? 16 minus 3 squared, that's 9. 16 minus 9 is 7. And so on and so forth. Okay, so if we look at each example here, all right, do you see the pattern? Here in the first example, let's look at k. In the first example here, k is 0. So what is this? 1 squared minus 0 squared, that's k plus 1 squared minus k squared. Okay. When k is 1, I get 2 squared minus 1 squared. Again, that's k plus 1 squared. 1 plus 1 is 2, minus 1 squared. When k is 2, I get 3 squared minus 2 squared. Again, that's k plus 1 squared minus k squared, and so on and so forth. So if you kind of do the first couple of numbers, you sort of see the pattern emerge. Okay, and you see that every odd integer can be written as a difference of 2 squares if I write it as k plus 1 squared minus k squared. Okay. All right. Okay. All right. Any other questions on this problem? Okay. What other homework problems did we have here? Let's see. Somebody asked for a problem from 1.5, number 9. Give me a second here. Okay, so were you going to do it in another way? No, I was not going to do this problem in another way. Okay. All right. So we have here section 1.5. Somebody's asking on number 9. Okay. Part G, I believe, was the question. All right. Okay. So you're given this propositional function, L of x comma y, which stands for x loves y. Okay. The domain consists of all people. Fine. Write the following as a logic expression. Or it says use quantifiers to express each of these statements. Fine. So the statement you're given is the statement: there is exactly one person whom everybody loves. Okay. All right. So this problem has this quantifier here, exactly one. Okay. So that's not really universal. It's not really existential, right? Existential says that there is one, but it could be more. Okay. So we have to sort of limit this to just one person. All right. So let me show you how to do that with this problem here. Okay. So the way we say that there's exactly one, anytime you have a sentence that says there's exactly one, you want to write it as a logic expression with quantifiers. Okay, you first start by saying that that person exists. There exists somebody. There's at least one person, okay, that has the desired property. So we want to say that there's at least one person whom everybody loves. Okay, so we start with that. All right. So we're going to start by writing. Okay. I'm going to start by writing, there exists some person X whom everybody loves. Okay, so there exists some person X such that for every person or for everybody Y, L of, we want to say there's one person whom everybody loves. So L of Y comma X. Okay. All right, so that's how we start out our sentence. We start by saying that there exists a person whom everybody loves. There's at least one person whom everyone loves. Okay, so far so good. Any questions on this part before I continue? All I've said so far is that there exists a person X, such that for all people Y, Y loves X. Okay, so there is a person whom everybody likes. Okay. Shouldn't the X and Y be switched? No, because I'm saying everybody loves X, right? The sentence is X. Well, the variables are not so important. So you know what? The variables are not important here, okay? I'm saying if I put X first, it means X loves Y. If I put Y first, it means Y loves X, whatever. The actual letter I use doesn't really matter, okay? Okay. The next part of the sentence is going to be to say that there is only one person. So there is no one else. So how do we say there's only one person? By saying there is nobody else. Okay. So we're going to do that with a conjunction. Okay. So to say that there's exactly one, we're going to say there's no one else. All right. How do we do that? We do that in the following manner. Okay. All right. So we say for all people, let's call them Z, for all people Z, okay? All right. If, so I'm going to make a conditional statement here, but let me write it this way first. If for all people W, okay, W loves Z, okay, then Z equals X. All right, so I'm writing this down and I'm going to explain what I've written in just a moment. So this is what our answer will look like. Okay, now let me explain what this means. We started off by saying that there is a person X whom everybody loves. Okay. Now we want to say that there's only one person that everybody loves. Okay. So how do we do that? We say basically the idea is to say that if there is somebody else who has that property, the desired property, that person has to be the same person as X. Okay, that's how we do it. So this says for all people Z, if everybody loves Z, then Z has to be X. Okay. So for all other people, if there's some person that everybody loves, that person has to be X, has to be the person we were originally talking about. Okay. So this is basically saying for all people Z, if everybody loves Z, right, then Z has to be X. Okay, so everybody loves X, and if there's some other person who everybody loves, that person has to be X. Okay, there can't be someone else. It has to be X. Okay. So two questions here. Is there another way to write this? There might be. Okay. Let me get back to that in a minute. Isn't that just saying the same thing twice? No, I'm not saying the same thing twice. So why? The first part of this sentence here is saying that there exists a person X, but because I'm using the existential quantifier, there could be more than one person, okay, that everybody loves. There is at least one person X that everybody loves. Okay. The second part of the statement limits it to only one person. It's saying that there is only one person whom everybody loves. Okay. All right. Is there no way to say this? Possibly there could be. There's also something called the uniqueness quantifier, which we didn't discuss, but I'll briefly mention it up. I believe it's written this way. Okay, this is the uniqueness quantifier. All right. It's used to represent the words exactly one. There is exactly one. So if you were allowed to use this quantifier, which we never discussed, but if you were allowed to use this quantifier, it would actually make writing this sentence much easier. Right? It would just say, there exists exactly one person X, right? You would just write it this way, such that for all people Y, L of X comma Y, and then you would be done. You wouldn't need the second half, okay? But since we never used that quantifier, you would have to do it the way we did here. Okay. Any other questions? Uh, 1.7, number 9. Okay, let's move on to that one. So for this one, you're asked to use a proof by contradiction. To prove that the sum of an irrational number and a rational number is irrational. So if we're going to use a proof by contradiction, we have to look at the negation of the given sentence. Okay, so the sum of an irrational number and a rational number is irrational. So the negation would be, it is not the case that the sum of an irrational number and a rational number is irrational. So if it's not irrational, then the sum would be rational. Okay, so let's start by writing that down. So the negation would be the sentence, the sum of an irrational number. Let's call our irrational number I, and a rational number, let's call that R, is rational. Okay, that would be the negation. Is not irrational, it's the same thing as saying is rational. Okay, and I'll call that S. Okay, I'll call the sum S. All right, so we're saying I plus R equals some rational number S. Okay. Let's see if we can find a contradiction here. Okay. So remember, I is our irrational number, R is rational. This is the statement that an irrational number plus a rational number is rational. Okay. How do we find a contradiction? All right, so let's see. Let's say I bring the R to the other side. I subtract R from both sides. What am I going to get? I'm going to get I equals S minus R. Okay. Now that's the same thing as writing I equals S plus negative R. So what do I have here? I have a rational number. This is rational. Plus negative R will also be rational. So I have a rational number plus a rational number equals to an irrational number. But we know, I don't know, do we prove this? That the sum of two rational numbers, I think we proved it, is always rational. Okay, did we prove that? Or did we do the product? No, okay, maybe we did it for the product of two rational numbers. Okay. The sum of two rational numbers has to always be rational. Okay, we can prove that quickly right now. Let's say I do A over B plus C over D. So let's say this is one rational number plus another rational number. Okay, it's rational. Okay, so I'm doing a quick proof for this, but so A, B, C, and D are all integers. B and D are not equal to 0. Okay, the sum has to be rational, right? If I add these together, I think we proved this. I could be mistaken. Yeah, I'm pretty sure we did. Okay, I'm just going to redo it quickly though. If I add this together, I'm going to get AD plus BC over BD, which is rational. Okay, it's an integer divided by an integer, and the denominator can't be 0. Okay, so the sum of two rational numbers has to always be rational. Okay, but according to this equation we have here, I have the sum of two rational numbers equals an irrational number, because I is irrational. Okay, so this contradicts the theorem, I'll call it a theorem, that the sum of two rational numbers is always rational. Okay, so this is a contradiction. This is impossible. I can't have a sum of two rational numbers equaling to an irrational number. So therefore, this statement has to be false, and our original statement is true. Okay, and that's why I'll stop here. Questions on this problem? Okay. Are you confused? Okay, let's go over this quickly one more time here. So we're looking at the negated statement. The negated statement is that an irrational number plus a rational number is rational. If I play with this equation, I get an irrational number is equal to the sum of two rational numbers. But that's impossible, because the sum of two rational numbers has to always be rational. Okay, so this contradicts what we proved, that two rational numbers added together must be rational. So therefore, this statement has to be false. And our original statement is true, that the sum of an irrational number and a rational number is irrational. So therefore, the sum of a rational and irrational number is irrational. Okay. It can't be rational, because if it was, we would end up with a contradiction. Okay. All right, does that answer your question? All right, any other questions? Okay. Any other homework questions? All right. Let's now continue with where we left off in section 1.7. We are going to finish up 1.7 now. Maybe do a little bit in 1.8, and then we'll be finished with chapter 1. Okay, so we're still in 1.7. We're now going to discuss proving biconditional statements. And also we're going to discuss proving equivalence. Okay, so those are the two things we're going to discuss now. All right, so let's just start by talking about proving biconditional statements. Let's start with an example. Okay, so let's say I ask you to prove the following. Prove that n is odd if and only if n squared is odd. Okay, so here is a biconditional statement we want to prove. All right, if and only if. Now remember, a biconditional statement is equivalent to saying if P then Q and if Q then P. So it's really two conditional statements. So if you want to prove a biconditional statement is true, you have to prove that these two conditional statements are true. You have to prove that each proposition implies the other. Okay, so we need to prove. So you have to prove if P then Q, and you have to prove if Q then P. You have to prove both. Prove that and that are both true. Okay, so let's do it for this problem. If P then Q, let's say n is odd is our P, and n squared is odd, let's call that our Q. Okay, so let's start by proving if P then Q. We're going to prove the statement, if n is odd, then n squared is odd. Okay, so we have to prove this, and we can use any of the methods of proof that we've discussed. Let's do a direct proof. If n is odd, then n squared is odd. We might have even proved this in a previous class, but let's do it now. Okay, n is odd. We assume n is odd. If n is odd, then n equals to 2k plus 1 for some integer k. Okay. Let's see if n squared is odd. Okay, so n squared will equal to 2k plus 1 squared, since n equals 2k plus 1. That is going to be equal to 4 4k squared plus 4k plus 1. Okay, we need to show that that's odd, so I rewrite that as 2 times 2k squared plus 2k plus 1. That's 2 times an integer plus 1. That's odd by definition. And the first proof is done. Next, we need to prove the implication the other way, that if q, then p. So that would be the statement, if n squared is odd, then n is odd. Okay, this one I believe we proved in some form or another. Maybe we proved it for even integers, I don't remember. I think we did it for even integers. Okay, so we're going to prove this one. Again, instead of a direct proof, since this time the hypothesis has a more complicated expression, has n squared, right, and the conclusion has just n, let's try a proof by contraposition. Okay, so let's do proof by contraposition. So we're going to prove that if n is even, n squared is even. Okay. So this is the one we're going to prove, the contraposition. All right, do a direct proof. Assume n is even. If n is even, then n equals to 2 times k for some integer k. Okay. All right, square both sides. You get n squared equals to 2k squared. 2k squared is equal to 4k squared, which is 2 times 2k squared. So n squared equals to 2 times an integer. It's even by definition. So we've shown that n squared is even. Okay, this proof is done. So we showed that when n is odd, n squared is odd, and we showed when n squared is odd, n is odd. Okay, so our proof is complete. We now know that n is odd if and only if n squared is odd, that each one implies the other. And our proof is done. Any questions on that?
So, I have a question.
Yes.
So for the second part, we have used a proof by contraposition, but can we use a direct proof and work backwards as in part A? Like I use the same expressions and work backwards to get the same thing, to get n, like 2k plus 1 format.
I'm not 100% sure what you mean, because if you work, I think if I understand you correctly, what you're saying is you're working backwards. If I understand what you mean correctly, you're saying prove that if n is odd, then n squared is odd. But that's what we proved in the first part. We're not saying that now. We're saying something different. We're saying that n squared is odd, n is odd.
Like, sir, if I take the last line from the first part, that is 2 times 2k squared plus 2k plus 1. If I show that this is equal to 2k plus 1 format, does that work? No.
I have to see what you mean. I'm not 100% following what you're saying, but I think if I understand you, if I think I understand you correctly, that would not work. But if I saw it, I might be I'll see that I'm misunderstanding what you're saying.
Okay, sir.
Okay. Any other questions? Please scroll up a bit. Yeah, I can scroll up. There you go. Okay. No problem. Any other questions? Okay. All right. Let's now talk about, so that's how you prove a biconditional statement. Let's now talk about how to prove a statement that says a bunch of propositions are equivalent to each other. Okay. All right, so sometimes a theorem states that several propositions are equivalent. Okay, so you'll have a theorem that will say all of the following statements are equivalent to each other. All whenever that happens, what does that mean? If I say a bunch of statements are equivalent to each other, well, what does logical equivalence mean? That means that when one is true, they're all true, and if one is false, they're all false. They'll have the same truth values. All right. So in other words, what we're being asked to do is show that when one is true, as I just said, they're all true, and when one is false, they're all false. All right. So this is the same thing as proving the following. To prove they are equivalent, all right, we create a series of conditional statements. Okay. And prove that they're all true. Okay. So for example, let's say you had a theorem that says the following are equivalent. Okay, and it gives you a list of propositions. Let's say P1, P2, and P3. Let me call them 3 propositions. Yes. Okay, so in this example, we're going to have 3 propositions. So the following are equivalent, P1, P2, P3. Okay, so what we do is we're going to create 3 conditional statements that are, so to speak, going to circle through all the propositions. Okay, if these are all equivalent, then that means when P1 is true, P2 will be true. Okay, and that also means that when P2 is true, P3 is true, and when P3 is true, P1 is true. Okay, so I create these 3 conditional statements where I start with my first proposition and I work my way until I come all the way back to the first one. Okay, I go almost like in a loop, in a circle. I start in the beginning and I circle through all of them. Okay, now if one is true, they will all be true, and if one is false, they will all be false. Okay, so let me show you, let me demonstrate this with an actual example. Let's say I tell you the following. Show that the following statements are equivalent. Okay. By the way, saying that they're equivalent is basically saying that they're all one big biconditional statement. Okay. Okay. So 1, n is even. Okay, that is a proposition. 2, n minus 1 is odd. And 3, n squared is even. Okay, let's say I give you these 3 propositions, and then there could be more than 3. There could be 2, 3, 4, 5, 6. Okay, we'll start with 3. So show that the following statements are equivalent. N is even, n minus 1 is odd, n squared is even. Okay, so as I said before, what does it mean that they're equivalent? That means that if one is true, they're all true. Okay. All right, so to prove that they are all equivalent, we create 3 conditional statements. We're going to call the first one P1, the second P2, and the third P3. Okay, so we start by showing that when the first one is true, the second has to be true. P1 implies P2. Okay, what is that statement? Let's write it down. That's the statement: if n is even, n minus 1 is odd. Okay, so we have here a conditional statement. Let's prove it by direct proof. N is even. We assume that that's true. So if n is even, then we know by definition n equals to 2k for some integer k. Okay, we need to show n minus 1 is odd. N minus 1 will be equal to 2k minus 1. Right? If n is 2k, n minus 1 is 2k minus 1. So I have to show that that's odd. We always have to go back to the definition. To be odd, it has to be 2 times an integer plus 1. So I can rewrite this as 2 times k minus 1 plus 1. Right? That's the same thing, right? If you distribute, you get 2k minus 2 plus 1 gives us back 2k minus 1. So I have here 2 times an integer plus 1. That's odd by definition. Okay, so the first proof is done. We showed n minus 1 is odd by definition, by direct proof. Yeah, you should write that every time. Well, you have to prove that it's odd. We never proved that it was odd. We know that 2k plus 1 is odd. We have now proven that 2k minus 1 is also odd. Okay. From the definition, somebody asked where did the plus 1 come from? That's from the definition. How did I get it? Oh, how did I get it? You're asking. Okay. Remember, by the definition, something is to be odd, it has to be 2 times an integer plus 1. It has to look like this. That was definition of odd integer. So I just algebraically manipulated it to get this. This is equivalent to this, right? I get 2k minus 2 plus 1. If I distribute, negative 2 plus 1 is 2k minus 1. All right, so you just got to use your math knowledge there. Okay. Like I said, sometimes you have to be a little creative. All right. Proofs require a little bit of creativity sometimes. Okay. Okay. Let's move on to the second proof. We now have to show that when P2 is true, P3 will also be true. So that's our second conditional statement. If P2, then P3. Okay. Okay. What's that statement? That would be the statement. P2 is n minus 1 is odd. P3 is the statement n squared is even. That's the statement. If n minus 1 is odd, then n squared is even. Okay, let's prove this. Let's again try a direct proof. So we're going to assume n minus 1 is odd. If n minus 1 is odd, by definition, we get n minus 1 equals to 2k plus 1 for some integer k. Okay, I won't write it this time, all right? But it's for some integer k. All right, let's see if n squared is even. Okay, so first I have to see what n is equal to. So let me add 1 to both sides. If I add 1 to both sides, I get n equals to 2k plus 2. Now let's square both sides. N squared will equal to 2k plus 2 squared. That's going to be 4k squared plus 8k plus 4, I believe, if I did that correctly. It's 2k plus 2 times 2k plus 2. We want to show that this is even. So what I'm going to do is factor out a 2. I get 2 times 2k squared plus 4k plus 2. I've got 2 times an integer. N squared is even by definition. And this proof is now done. Okay, we showed that when n minus 1 is odd, n squared will be even. Any questions on part 2 before we move on to the third and final part? All right, now we need to show that we have to circle back to the beginning. So we have to show that when P3 is true, P1 is true. Okay, what was P3? P3 was the statement n squared is even. So this is the sentence, if n squared is even, then n is even. Which I think we've already proved, but let's do it again. If n squared is even, then n is even. Okay, yeah, I believe we proved this one. We proved this on last time, right? When we were doing the proof that the square root of 2 is irrational. I'll do the proof again very quickly. Let's do a proof by contraposition. Okay, so we're going to prove the contrapositive. The contrapositive is the sentence if n is odd, n squared is odd. Okay, we assume n is odd. All right. what will n squared be? Let's see. N squared will be, if I square 2k plus 1, I get 4k squared plus 4k plus 1. That's equal to 2 times 2k squared plus 2k in parentheses plus 1. That's 2 times integer plus 1. That's odd by definition. Okay, so the proof is complete. All right? And that's the end of this proof. Okay, it would be the same thing, let's say, if we had 4 propositions instead of 3, right? We would show that the first one implies the second implies the third implies the fourth, and the fourth implies the first, right? We create a loop. Okay, we have conditional statements. Okay. You're having trouble with that sometimes. So I suggest you go over the problems we've done in class and the homework problems as well. Because once you've seen them a couple of times, you sort of get a feeling for how a lot of these things work. Okay. Not every problem is the same, but it'll sort of help to give you a feeling for how they work. Okay. Any other questions? No, you don't have to do any more. Once you do this, this is fine. If you want to write a conclusion just to summarize what you've done, that's fine. But, you don't need to. Okay. Okay. Let's now discuss a couple of things from section 1.8 to wrap up chapter 1 here. Okay. So section 1.8, proof methods and strategy. All right, so let's discuss something called existence proofs. All right. Sometimes you have theorems or statements that basically state that something exists. There is something, something exists, okay? In order to prove theorems like that, you really just need to do, well, you can do it in one of 2 ways. You really just need to show that the thing we're being asked to show exists. Okay. All right. So a proof of a proposition of the form, there exists an x such that p of x, right? So I have some theorem that's existentially quantified. It says there exists some x such that p of x. Okay. Proofs of statements like this are called existence proofs. So a proof like that is called an existence proof. Right? Why? Because you are proving that the thing exists. That's how you're going to show the statement is true. Okay. So there are 2 ways that we can do an existence proof. So there are 2 types of existence proofs. Okay, constructive and non-constructive. Okay, so one constructive. All right, a constructive existence proof is where you actually find the thing you're looking for. Okay, you show it exists. All right, so constructive existence proof. This is where you prove the statement by finding an element in the domain for which p of x is true. Okay, Okay, you actually find an element, find a number x or an element x such that p of x is true. Okay, if you do that, that would be a constructive existence proof. There's also something called a non-constructive existence proof. Okay, in a non-constructive existence proof, you don't actually find the element x for which p of x is true, but you somehow show that it has to exist. Okay, so you don't find the element x, but you demonstrate it has to exist. Okay, and that can be done in a couple of different ways. Right. So let me give you an example of a constructive and a non-constructive existence proof. Let's start with constructive. All right, so we want to show that there is a positive integer that can be written as the sum of two cubes in two different ways. Okay, so for this one, I'm going to give a constructive existence proof. Show that there is some positive integer that can be written as the sum of two cubes in two different ways. Okay, so the proof. So what is a constructive existence proof? I just have to find the number. I have to show you the number, show you that I can do this. So I'm going to just give you the number. That's my proof. I give you the example. So the number I'm going to give you is the number 1,729. I can write this as the sum of two cubes in two different ways. I can write this as 10 cubed plus 9 cubed. Or I can write it as 12 cubed plus 1 cubed. Okay, so I took my number, I wrote it as a sum of two cubes in two different ways. That's a constructive existence proof. I showed you the number. I gave it to you. Here it is. Okay, I showed you that the element exists, the number exists. Okay, any questions on that? All right, now let me show you how a non-constructive existence proof might look like. Well, no, for this one, that number you would have to come by after considerable calculation. Just for the purposes of this example, I'm just giving it to you, all right? Because it would be very hard to figure that out on your own. Okay, and on an actual question, I would give you something you could figure out on your own. Okay. Okay, so an example of something now that uses a non-constructive existence proof, okay? So show that there exist irrational numbers, x and y, such that x to the power of y is rational. So we're going to give a non-constructive existence proof, meaning I'm not going to tell you what the numbers x and y are, okay? But I'm going to show that there has to be numbers x and y such that are irrational, such that x to the power of y is rational, okay? All right. So let's start by considering the square root of 2, right? We already know that the square root of 2 is irrational. We proved that. Okay. All right, so let's say x and y are both equal to the square root of 2. All right, so then x to the y will be equal to the square root of 2 to the square root of 2. Okay, so this is an irrational number raised to the power of an irrational number, right? We have two numbers, x and y, that are irrational. Okay, and now I do not right now know if the square root of 2 raised to the power of the square root of 2 is irrational or if it's rational. Okay, if this number, if the square root of 2 to the square root of 2, if that's rational, we're done, right? We found such a number. If this number is rational, then we have two irrational numbers, x and y, with x to the power of y rational. Right. Okay, and we're done. We have our answer. But I don't know that it's rational. It could be irrational, right? It's one or the other. Okay. If the square root of 2 to the square root of 2 is irrational, right, then we have not yet found the number we want. So if it is irrational, let x equal to the square root of 2 to the square root of 2. That's an irrational number, if it's irrational. And let y equal to the square root of 2. Okay. So that x to the y would now be the square root of 2 to the square root of 2 raised to the square root of 2. Okay, so this is again an irrational number. If square root of 2 to the square root of 2 is rational, then this is an irrational number raised to an irrational number. Okay, let's simplify this. What is this equal to? Well, I have a power raised to a power. By the laws of exponents, I multiply the powers. So this is the square root of 2 to the power of the square root of 2 times the square root of 2. The square root of 2 times the square root of 2 is 2. So I have the square root of 2 squared, which is 2, which is rational. Okay, so either way I go, if the square root of 2 to the square root of 2 is a rational number, as was in the first part here, then I have my answer. And if it's irrational, then just let x equal to the square root of 2 to the square root of 2. Let y be the square root of 2. And I have an irrational to an irrational, which is rational. And I have my answer. Okay. So I don't know which one is correct, because I don't know if the square root of 2 to the square root of 2 is actually rational or not. But I know it has to be one of the two. Okay. So either way, I can find two irrational numbers, x to the y, that are two irrational numbers, x and y, such that x to the y is rational. And I'm done. Okay. Final questions on this. Let's see. Okay, so again, this one is non-constructive because I don't know which one is the correct one, but I know it has to be one of the two. Okay. All right, any final questions on that? All right, if there's no final questions, we will end here for today. And I will see everybody tomorrow. All right, let's take the attendance. Everyone let me know you were here, and then you can go. Okay, I'm gonna head out. Take care, everybody.